The last section in this unit is going to be to look at some particle motion applications, which you've seen before, but we're going to include now the parametric functions, the vector valued functions, a lot of the new stuff that we've seen in this unit. So here is your first example. We have this graph right here. It says a particle starts at point A on the positive x-axis at time 0 and travels along the curve from A to B to C to D as shown above. The coordinates of the particle's position, x of t, y of t, are differentiable functions of t, so these are parametric, where x prime of t, dx dt, is equal to negative 9 cosine pi t over 6 times the sine of pi square root t plus 1 over 2, and y prime, dy dt, is not explicitly given. At time t, the particle reaches its final position, point D, on the positive x-axis. Okay, first question. The line tangent to the curve at the point x of 8 and y of 8 has equation y equals 5/9 x minus 2. Find the velocity vector and the speed of the particle at this point. Now, a couple of examples worked their way into these notes, and I forgot to take them out. We are not ready to talk about speed yet. That's coming in a later unit, so we're just going to answer the part about the velocity vector, okay? So two things that we can take from the information that was given. If we are looking at the point x of 8, y of 8, this tells us that t is 8 because it's x of t, y of t, right? Second thing is that if the tangent to the curve has this derivative, then we know that dy dx has to equal 5/9. Okay? So that is the first thing that we know. Now, we also know that we want to find dy dx at t equals 8. We know that that is equal to 5/9, but let's think generally how we would find that, because essentially we need to solve for y prime of 8. That is what we don't know. We know dy dx, so we know essentially y prime over x prime. We know how to find x prime of 8, but we do not know how to find y prime of 8. So we can go ahead and set up dy dx the way that we know we would find it. So if we want to evaluate dy dx at t equals 8, that's going to be equal to y prime of 8 over x prime of 8. Well, we don't know what y prime of 8 is. We do know what x prime is. It was given to us, so we can plug that information in. So we've got 9 cosine of 8, I'm plugging in the wrong spot. Pi times 8, so this will be 8 pi over 6 times the sine of pi times the square root of 8 plus 1, so it's going to be times 3 over 2. Okay, we didn't have to find x prime because it was given to us. Well, if we plug all of that information in, we know that y prime of 8 is equal to the negative 9 times the cosine of 8 pi 6, which is 4 pi thirds. That's going to be negative 1/2. And then times the sine of 3 pi halves, which is negative 1. And so when we cook all of that down, we end up with negative 9 halves in the denominator, which is going to bring us to 2y prime of 8 over negative 9. That is how that kind of works out. What do we know about this? We know that 2 times y prime of 8 over negative 9 should equal 5/9. We know that, which means if the denominators are both 9, that means that negative 2y prime of 8 should be equal to 5. And so we get that y prime of 8 is negative 5 halves. So the velocity vector, v of 8, is going to be the velocity in the x direction and the velocity in the y direction. The velocity in the x direction, we had already figured out that that denominator was equal to negative 9 halves. That's the value that we got for x prime of 8. And then we figured out then that the value of y prime of 8 needs to be negative 5 halves. And so that's our velocity vector. So that one had a little bit of everything. Some parametrics, some vectors, all kinds of things there. So these are how they're tricky about asking you things, where you've got to pull information from different parts and that kind of stuff. That's always kind of tough. Now, we are going to skip these next two examples because, again, I didn't mean to include them. These actually require integration, so we will get to those when we get to our practice on integration later this semester. So if you turn to the next page, this one is multiple choice. So it says the position of a particle moving in the xy plane is given by the parametric equations x of t and y of t. At which of the following points is xy is the particle at rest? That means we want to know if it's at rest, then the velocity, which is our derivative, must be equal to 0. That's what we're trying to figure out. So will you go ahead and pause the video and try this one on your own, and I'll come back to you with the answer in 3 seconds. The correct answer is A, negative 412. We need to figure out the derivative, dy dt, and set that equal to 0. That would be where the top is equal to 0. And so you get the point t equals 2, which when you evaluate for x of 2 and y of 2, we get negative 412. We can double check here as well. If you plug in 2 to the denominator, you get 12 minus 12. So 0 over 0 is really what we are looking for. That means we're going 0 in the vertical direction, 0 in the horizontal direction. So in either direction, our velocity is 0. And so we are definitely at rest at that point. Okay? Example 4 says, for time t greater than 0, the position of a particle moving in the xy plane is given by the parametric equations x and y. What is the acceleration vector of the particle at time t? This is much simpler than having to find dy dx because we're just asking about vectors. So since those two equations are position, that tells us that our position vector is those two components. To get to acceleration, then, we need to look at the velocity vector. So we'll go ahead and take the derivative of s prime of t. So there's our velocity vector. Here's a little AP exam note. Make sure you cannot just switch to v of t without establishing this relationship that v of t is equal to the derivative of s. Essentially, it would just be like throwing in a new function name without telling where it came from. So making that statement that s prime is equal to v is really important. And then when we do the next thing, we're going to do exactly the same. When we say that v prime of t is equal to a of t, and now we can go ahead and take that derivative. So we're going to end up with 2 negative 18 over 3t plus 1 cubed. We're using some chain rule action there. Okay, so now we have our acceleration function. So if we want the acceleration vector, then we want a of 1. I don't know why my pen is writing funny. A of 1, and when we plug in those values, we get 2, because that one was constant, and we end up with negative 18 over negative 64, I believe. Hold on, I think I might have copied that wrong. I did. When we do this chain rule, this 18 ends up positive because you multiply by a -2 power. So that should be a positive 18, which makes this positive 18, and that is a positive 64. And that reduces down to 2 and 9, 30 seconds. That is our acceleration vector, okay? And again, the last two examples, oh, I did take those off. The last two examples, if you have an example 5 in your packet, we're going to skip that one for now because it requires integrals. We're just focused on derivatives right now. So that is a little bit of the types of questions you might see on particle motion when we're talking about vectors and parametrics.